All right, so this one, guys, to say it's important is probably the understatement of the school year thus far. This is one of the most important lessons that we're going to talk about, to be honest with you, almost the entire school year. Because what we're going to talk about in this portion of the notes or of the class is things called periodic trends. Periodic trends have everything to do with behavior, and chemical behavior is something that in AP chemistry you have to be very familiar with, understanding why things happen and being able to predict how things happen. And so periodic trends will allow you to be able to do that. So, what we previously did just a few days ago was a lot of electron configurations and things like that. And that's going to matter. A lot of that stuff factors in here. So that's why I say the periodic table, colon, it's not just for electron configurations anymore, because we're going to use it. So this is something that you guys should remember from general chemistry. Both myself and Mr. Wolf tend to cover this in very great detail, but you really need to know all of that detail. So this is one where whatever questions you have, whatever things that maybe you're not 100% understanding throughout this lesson, make notes of your questions. Make sure that you come back tomorrow and have things to talk about if you have those questions, because this is something that is, let me stress again, is really important. Okay, got it? All right, good. Okay, so I don't do learning goals for every single lesson, but for this one, I just want to give you a few to kind of make sure that we're clear on kind of what we're going with and what we're doing. So first, you should know what an ion is. You should know how it can be formed. You should know why ions form. Those are things from general chemistry that hopefully are clear. I should know, or you should know, the typical ionic charge of all S and P block elements. That's something that really you should have done already. And you should know why transition metals are difficult to predict in terms of ionic charge. So these are things that we would have done already. So having an idea of this is very helpful to start. And then for part two, which is really the part that we're talking about right now, we're going to define periodic law. We need to know, what does periodicity mean? Number two, you can see that there are, in the white writing, 4 different periodic trends that we're going to need to know a great deal of information about. Atomic radius, ionic radius, ionization energy, and then electron affinity, which is the more college term that they use, but it's the same thing really as electronegativity. There's a little different measure of the two, but essentially it's the same thing, same definition. And so notice in number 2, I'm asking you to determine the trend by using the periodic table. But in number 3, I'm asking that you need to define it. You need to know exactly what it is, as well as why the trend exists. And so that's where the big portion comes in. So if you're ready, we're going to hit learning goal 1 here, periodic law. So periodic law, like I've said a couple times here, also known as periodicity, it has to do with basically the way the periodic table is set up. As the definition states, when elements are arranged by increasing atomic number, their chemical and physical properties will vary periodically. That's the book definition, but in my opinion, something in there is a little tricky. It's that word periodically. They vary periodically. What the heck does that mean? So I'd like to simply state it for you. There are repeating trends. If you move from left to right across the periodic table, there will be trends that repeat themselves as you move to the next line. Similarly, if you move up, from top to bottom, you will also see repeating trends as you go through each column. And so these are, again, this is what it means by varying periodically. So we did an activity with the cards, and we kind of were able to understand how all of these things were kind of varying, like up, down, and that's periodic law or periodicity. So there are a few, which we've already talked about, a few chemical physical properties that we're going to need to look at. That includes ionization energy, ionic radius, atomic radius, and again, electron affinity, also known as electronegativity. So before we get into the real nitty-gritty, we need to make sure that you know stuff about ions. So quick review here. So you should understand all of this. An ion has a negative or positive charge, and you form it by either gaining or losing electrons. Why do they gain? Why do they lose? You tell me. I'm listening. Are you telling me? Yeah, I'm not sure. I can't actually hear you. So I'll tell you the answer. All atoms, as written on the periodic table, are unstable. Unless you're a noble gas, you aren't really comfortable in your own skin as an atom. There's sort of just something inherently wrong because you want that octet and you don't have it. It's, I guess, kind of like you want a boat and you don't have a boat and you're upset about not having a boat. So darn it, we're going to go out and get ourselves a boat. So what happens is the getting of the boat is the gain or the loss of electrons in order to reach that octet to become stable. Do you like the boat example? I kind of thought it was funny. Okay, so what governs whether atoms gain or lose electrons? Well, essentially, it's a game of numbers. It all is based on the octet rule, but it's however it's going to get there easiest. So, for instance, aluminum. Aluminum has a choice here. Aluminum could choose to lose 3 electrons, and then it would emulate neon's electron configuration. Or aluminum, I suppose, could choose to gain 5 and be like argon. Well, simple game of numbers. Which is easier, losing 3 or gaining 5? I think 3. So that's why it says atoms gain or lose electrons to have the electron configuration of the nearest noble gas, because it's just simply ease. Way easier to lose 3 than try to go and round up 5 more. Excuse me. So if an atom gains electrons, it will become negative because electrons are negatively charged. It will be called an anion. And a cation is the name for the positive charge, which is going to occur when you lose electrons. So all of that is stuff that you should know, just a quick review, so that we're just clear. So are you clear? Good. All right, moving on. Atomic radius. Atomic radius. So you probably know the word radius as opposed to, say, the word diameter. So you would understand that it's, essentially from the middle of an atom to the outside edge. So you have half the distance, basically. But here's a problem. Where does an atom end? Where does an atom end? It is difficult to measure the exact radius of atoms because electrons do not end abruptly. So do you recall that electrons are held within these electron clouds? And electron clouds, you sort of know if you're in it, kind of like a fog. But as you begin to move towards the edges of the electron cloud, it becomes a little tricky. Am I in it? Am I not? It's sort of like a half fog. So it's a little tricky to figure this out. So in order to determine what the actual atomic radius is, what they use is something called the covalent radius. So in the picture here, you can see that there are apparently 2 bromine atoms that are covalently bonded together. The black dots in the middle are the nuclei of each of those atoms. And you can see that it gives you what is called the internuclear distance. In other words, it's called the bond length. So the length between the 2 nuclei from here to there is 228 picometers, which is a very, very, very small unit of measurement. And then they say here the covalent radius is 114 picometers. So how are those 2 numbers related? Ah, yes, that is half of that, which means that they're essentially measuring from here. Sorry, I lost my cursor. From here to here. So you can see the definition: distance between 2 nuclei of atoms that are chemically bonded together. They have real functional distances to work with instead of this like foggy ending. So that's actually how they measure atomic radius, for your information. So the general trend in atomic radius is as follows. So I'll give you the wording of it, which you can certainly pause the video if you would like to take a moment to read that. But generally, what I like to do is show you a periodic table and then give you one trend line. In textbooks, they generally give you 2 trend lines. They'll give you one going up and down and one going side to side, and sometimes they're just kind of confusing to look at. So I found that the easiest way to do it is just one trend line. So if you take a look at the whole periodic table, fluorine, and again, I'm kind of intentionally leaving a few things. Oh, sorry. I'm not saying fluorine is the absolute smallest. In fact, hydrogen is the absolute smallest. Helium is very small also. But when you just look at the general trend line, the things that are in the upper right-hand corner in that non-metal area, those are going to be the smallest. And then as you move diagonally down into the left bottom corner, for instance, cesium here, that's where you get the biggest ones. So it's a general type of a trend. It's not 100% perfect, but it's pretty darn good. So again, do keep in mind, yes, hydrogen is very small. Helium is very small too. But part of the problem is these noble gases were supposed to be measuring atomic radius by covalent radius. Well, most of our noble gases don't covalently bond, so it becomes kind of tricky to exactly get an atomic radius for those noble gases. So this is your general trend line. So this is half of the story, basically, to understand the trend and how it works. The other half of the story is why. And this is the big part. So these are the parts in which I would definitely say to you, if you have questions, make sure that you are jotting them down so you can come back and ask me. So the reason is something called effective nuclear charge and something called shielding. As we move forward with our periodic trends, we are going to be talking about effective nuclear charge and shielding. Oh my goodness, a whole lot. So start getting used to these words. ENC is an appropriate abbreviation for effective nuclear charge. So what the heck are these? Well, effective nuclear charge is the positive charge that an electron experiences from the nucleus. So think about what's in the nucleus. It's this core of positive charge with protons, and the electrons are on, excuse me, and the electrons are on the outer fringes. And just like magnets attract, the positive core will attract the negative electrons and pull them inward. So that's what we're talking about in just very brief ways. As you can see, full discussion. Next slide. The effective shielding also must be taken into consideration, and you're going to see a full description of shielding also in a couple of slides. But these two things work together. Bell. Ding. One more. Okay, good. All right. So increased ENC, meaning more effective nuclear charge, will end up decreasing your atomic radius. And that's because, as you see in the parentheses, electrons are being pulled in more strongly by the nucleus. If you increase shielding, you will be increasing the atomic radius. And the reason for that is because valence electrons don't feel the pull from the nucleus as much, and they can move outward. So at this point, depending on your recollections from last year, you may or may not understand the two green statements well or not. Definitely make sure that you understand those green statements, but I will explain in more detail in the next two slides. So you're kind of getting the end of the story, and now I'm about to fill in all the blanks. Okay, so to specifically focus on ENC, what I would like to do is present to you 4 atoms. So you can see we have lithium, beryllium, boron, and carbon. The 3p, 4p, 5p, 6p inside represents what's inside the nucleus. So this very inner ring right here should be kind of a darker, heavier line. That's the nucleus. And then this would be the first energy level containing 2 electrons. And then this would be the second energy level that contains 1 electron. And so you can see as you move progressively up on our atoms that we are producing additional, or that we now have additional electrons in that last energy level. So that's really the only difference between these. They've got an extra proton and an extra electron. So as you move across a period, shielding will stay the same. So just kind of take that for what it is right now. As you move across the period, shielding will stay the same. So across the period means, again, left to right. Shielding remains constant. And that's because they have the same number of energy levels, which is 2. But the valence electrons increase, right? So as I go from lithium to beryllium to boron to carbon, I am increasing by 1 valence electron every single time, effectively making the nucleus more positive. Well, give me a second. So here's a little math problem. You will never be asked to do this math, but what I want you to understand is why, when we say the ENC is 1 or the ENC is 5, why that is the case, where that number actually comes from. So you can see in the little green box here, 3 protons, which is the 3 protons, of course, in the nucleus, and then the 2 electrons. Those 2 electrons are these inner electrons. They're the first energy electrons. They're called core electrons. And that only leaves my 1 electron, my 1 valence electron, kind of out in the dust. So you do a subtraction here. So the 3 protons minus 2 core electrons will give me an ENC of +1. Okay, so there's 1. If I go down the line to beryllium, you can see that I've changed it just slightly, because the only thing that really changes here is protons, because this 2 electrons right here, again, that's the core electrons, and core electrons, by the way, are anything that's not included in the valence. So only the outer energy level doesn't count. So in this case, 4 minus 2 gives me an effective nuclear charge of 2. So what that means is these 2 electrons in the valence of beryllium are feeling a stronger pull from the nucleus. Okay, these this valence electron for lithium is only feeling an effective nuclear charge of 1. And think of, as these numbers go up, the nucleus is getting stronger and stronger. It's pulling harder. So for lithium, the pull is 1, which is, strong, but not that strong. Beryllium has a pull of 2. And that's a little stronger, which means that the beryllium is actually going to be sort of sucked in. That outer electron level will be sucked in a little bit tighter. When you look at boron, you can see again that the only change here is the proton number. So 5 minus 2 equals 3. So boron is even smaller than beryllium is, because the valence level is feeling more pull from the inside. And it's all based on, as you're seeing here, it's just based on positives and negatives and how they attract to each other. So as you can see then, carbon, 6 minus 2 is 4. So those 4 valence electrons in the outer energy level of carbon are feeling a pretty strong pull inward, which makes of this group carbon the smallest of these atoms. So as you move from left to right, you do become smaller. When you take a look at maybe again why this is all happening, the nucleus draws the valence electrons in to try to negate or get around this extra positive charge that it's feeling, and so the atomic radius gets smaller. So again, the ENC is sort of like this additional pull from the nucleus, because it's trying to kind of rein in or grab a hold of these valence electrons and not let go of them. So again, hopefully that makes some sense. We'll continue talking about it though, so definitely jot down any questions that you have, and we're going to go ahead and talk about shielding and what the heck shielding is. Okay, so this is our slide for shielding. Moving down a group. Atomic radius gets larger due to shielding. So what is shielding? By definition, it is related to increases in valence electrons. Any electrons. Increases in any electrons. Hence occupied orbitals. So if you think about a Bohr model with just the circular orbits, which in fact on the previous slide, again, these right here, these are Bohr models with just these circular orbits. So when you look at shielding, basically every single one of those additional orbits that you put around the nucleus is like a shield. So they, as you can see in the definition, they shield valence electrons from being drawn into the nucleus, and so atomic size increases, because if you have more energy levels, the nucleus, imagine the nucleus has arms, and the nucleus is reaching out, trying to grab a hold of these valence electrons. By the way, I'm doing this movement as I talk. So reach your arms out and act like you're trying to grab a hold of something, and it's just a little too far away, and you can't quite grab a hold of it. And so if you can't quite grab a hold of it, it can get away a little bit. And that's what happens with atoms. So in these two examples, you can see sodium and potassium. Notice where they are on the periodic table. Sodium is in the 3rd period and potassium is in the 4th. And you can see, I think pretty clearly in the pictures, that potassium has an extra energy level. And that is an extra shield that allows the nucleus to not have as strong of an influence on this valence electron out here. Notice the distance. This nucleus has to try to influence this electron. It's a lesser distance. This one has a greater distance. So the greater the distance between the nucleus and the valence, the more shielding is happening. And the shielding, of course, is occurring because of these literal shields. These are individual energy levels that act as shields, and that sort of allows this guy to sort of get a little bit out of control, to go outward a little bit. So hopefully these help. More filled orbitals, so more electrons in the core to shield valence electrons from being pulled towards the nucleus. So as you move down, if I go down one more to rubidium directly under potassium, you can see that it's in the 5th period, which means it's got 5 occupied energy levels, which means it's got an extra shielding energy level, so it's bigger. Cesium below that has 6 energy levels that are occupied, and 5 of those are shielding energy levels. So as you move downward, more energy levels are added, and that relates to then increased shielding, which is going to create a bigger atom. Please understand that it's not appropriate to say that sodium is bigger. It's not appropriate to say that potassium is bigger than sodium because potassium has more electrons. That's not enough. You'll never get credit for that. What you must say is that potassium is bigger than sodium because there are more electrons in more energy levels, and those additional energy levels shield the valence from the pull of the nucleus, and that is why potassium is bigger. So you'll have to start recognizing that in AP Chem versus General Chem, that your descriptions have to be very detailed and they have to be very specific, and that's what the graders of the AP exam are always going to be looking for. And if they're looking for it, then I'm going to be looking for it. So again, if you have questions, please make sure that you're recording them, that you come back to me tomorrow with these questions so that I can help you guys out. So we're going to continue to use the ideas of ENC and shielding as we continue. So hopefully it makes at least a little bit of sense. And we'll continue on to atomic radius. So with atomic radius, it's going to be similar to atomic. Ionic is it's a little different. In fact, it's a little bit more of like there's more wiggle room. It's not as perfect. So similar to atomic in general trend, but it is governed by whether you're a cation or an anion. If you are an anion versus a cation, you're always going to be bigger versus smaller. Always, always, always. If you compare ions to the atoms that they were formed from, okay? Comparing ions to the atoms that they were formed from. So for instance, if I'm going to say chlorine versus its ion, the chloride ion, Cl negative. Negative ions are always larger than their atoms. Positive ions, so again, think sodium, and then we're going to form the sodium ion, Na+. That sodium ion will always be smaller than the atom that it was formed from, so the sodium atom itself. And of course, my next question is going to be, why? Why would a negative ion always be larger than the atom it was made from? Well, it's a lot like a tug of war. If I get technical, it's the reduced effect of effective nuclear charge, and the electrons outnumber the protons. But if I explain that in maybe an easier way, it's literally a tug of war. So what happens now, you've added an electron to the atom, and that electron is now not in the same ratio with the protons anymore. Keep in mind, all atoms, as listed on the periodic table, are neutral. You have the exact same number of protons as electrons, which means that those numbers cancel out and make the overall charge of the atom 0. Well, if I start adding electrons, now I have an imbalance. And right now, I've got more electrons than I do protons. So please picture in your head a tug of war. And on one side of the tug of war rope are all the electrons. And on the other side, there's all the protons. Well, as we just said, we're forming a negative ion. So that means that the electron team has one more than the proton team. So does that make sense then? The electrons win the tug of war. So what happens if the electrons win is they can pull out, they expand out from the nucleus even further because the protons, plain and simple, just can't compete anymore. They can't pull on all those electrons because the electrons outnumber them. So it's exactly the same for the positive, but obviously the opposite. So for your positive ions, you have an increased effective nuclear charge because now the protons are outnumbering the electrons. So in this case, the protons win the tug of war. And that's not because you're adding protons, of course. When you form a positive ion, you remove electrons. And so now, if you imagine a perfectly balanced tug of war game, electrons and protons, same number of players, but now I'm going to take a few of the electron players away. Well, now who's got more on their team? Protons. Protons are going to win. So what that causes is overall the protons are now able to impact the electrons more. They're able to pull in even more than they were before, and that's going to shrink the size down because the protons now, just plain and simple, have more power over the electrons. So again, hopefully that makes sense. When comparing ion to ion, and I'll tell you right now, this statement is not exactly true. It will generally be true for anything that you're going to see on a test, but I'm telling you right now, you're going to yell at me because we're going to look at things in a textbook and it's going to be different. But most negatives, most ions that are negative will be bigger than positives. Not all. I know what the statement says. It says all. But this is one that's a little bit tricky to work with. Cesium, for instance. Okay, cesium is a gigantic atom. Even when it forms a positive ion, it's still pretty big. And it's still going to be bigger than fluorine's negative ion. But you're looking at sort of the two extremes. And so in those cases, it's not an all. But in a lot of cases, it's going to be a general trend that most of the negatives are bigger than most of the positives. So just take it for what it is. Don't quote me as that being law because I'm sitting here saying it's not. So to give you a picture, a very general picture. Oh yeah, why? Okay. So to give you a very general picture, please note the word very is in capitals because this trend is not perfect. It's something that if you compare a couple things to each other, you can pretty much get it, but it's a tricky one. So first off, you need to start here, which is just on the upper right side of the metalloid line. These are going to be negative ions, correct? So this is things like phosphorus, arsenic, selenium, tellurium. These are really big ions. So these are going to be your biggest, okay? Biggest right here. And as you begin to move then upward towards fluorine, so see the arrow upwards towards fluorine, you'll get a little smaller. So you're going to have smaller guys right up in here, okay? Now, if I kind of wrap it back around, you are also going to see relatively large cations here, and the absolute smallest cations are going to be here. So maybe the better way to think about this is in two segments, and I would almost suggest that that's how you think about it. I think it's the easiest way to think about. Okay, so you have negatives and positives, right? So your negatives are here in the corner, largest to smallest. Okay, and now you have your positive section. So all of these are positives, all the metals, right? All positive. Largest positives to the smallest positives. So what's kind of interesting about this ionic trend is that if you look at the negatives just on the one side of the metalloid line, they're going to be the biggest. And then if you look at these on the bottom side of the metalloid line, they're going to be the absolute smallest. So again, if you want me to do some more work with that, let me know. It's something that I can certainly talk about in more detail. Okay, so ionization energy, by definition, and it's incredibly important that you know the definition of this, minimum energy required to remove an electron from an atom in the gaseous state. So the gaseous state, maybe not a huge deal, but it's the removal of the electron. That's the most important part of the definition. You have to know the definition. So we're really talking about, forming ions, but we're talking about forming positive ions. So if you think about something like lithium, lithium only has one valence electron. Does it want that valence electron? No, not even a little bit, in fact. What it wants to do with that electron is give it away to somebody so that it can go back and be like helium's electron configuration. So the ionization energy, or the energy required to remove the electron from lithium, is slim to none. It's like lithium has the electron sitting in its hand, and it's holding its hand out, and it's saying, here, just take it. I don't want it. I won't fight you. Just take it. Very low energy required for that. But if you, on the contrary, take a look at fluorine, does fluorine want you to remove an electron? No. It wants to gain an electron. So fluorine, imagine fluorine has, let's go with chocolate bars, has 7 chocolate bars, which are going to equate to electrons. And so fluorine is pretty territorial over its 7 chocolate bars. And if you would try to approach fluorine and take a chocolate bar, it's probably going to fight you. It might pull out a knife or something. I don't know. It'd be bad. Don't try it. What I'm getting at is that the energy to remove an electron from fluorine is insanely high. It doesn't want to remove an electron. It doesn't want to lose one. It wants to gain one. It's the opposite. So when you start thinking about this, excuse me, in effect, I've already sort of explained a little bit of this. Ionization energy increases from left to right. So again, from lithium to fluorine, we just talked about how there's an increase in ionization energy. Group 1A, which is going to include lithium, has the lowest ionization energy because, as I just mentioned, they have 1 valence electron. They're happy to give that away. All they want to do is give it away, get the octet, be a noble gas. Additionally, they also have a very low effective nuclear charge. Their effective nuclear charge is 1. And by the way, I think I forgot to mention before, if you take out the D block elements and just look at your S and P blocks, to do effective nuclear charge across the periodic table, you just literally count up from 1. So in group 1, effective nuclear charge is 1. In group 2, it's 2. In group 3, it's 3, 4, 5, 6, 7. And then finally, your noble gases have an effective nuclear charge of 8, making their nuclei very, very good at pulling electrons in. So again, in group 1A, they have very low effective nuclear charges, an effective nuclear charge of 1, which also explains why ionization energy is the lowest, because if those valence electrons are not feeling the pull from the nucleus, which is again effective nuclear charge, then there's nothing really holding it on. You can pluck the electron off pretty darn easily. Noble gases have the highest ionization energies, and it's basically for 2 reasons. It's because of the octet being completely full, and they don't want to gain or lose electrons, and so they have their 8 chocolate bars, and they will fight you for them. And it also has the highest ENC of a +8, and so again, those electrons are held pretty much as tight as could be possible. So that's the general trend and an explanation of why. If you take a look at the periodic table, the general trend increases from left to right, it increases from bottom to top. And so if I were going to just, again, draw like one trend line, I would draw it from here up. Okay, from here up. So anything up in this corner is going to have your highest ionization energy. So I need you to do me a big favor, and this is going to require you to pause the video in a second. In your textbook, on page 328, there's a table, table 7.5. There are 2 big exceptions. Pause the video. See if you can figure it out. Where do you see these exceptions? Okay, so hopefully you've been able to maybe figure this out. If not, take a close look. Do you see exceptions between groups 2A to 3A and 5A to 6A? Do you notice it? Take a second and actually see if you notice it. 2A is a higher number, but what happens at 3A? It drops. Well, based on this trend line right here, it's supposed to increase all the way across. And so 2A is higher than 3A. And similarly, 5A, and if you track it, 3 to 4 increases, 5 increases, but then when you get to 6, it decreases. What the heck? What is going on? Well, something kind of funky. These are called pseudo noble gas configurations. 2A and 5A are relatively stable because, well, notice on the periodic table, 2A, that's the end of the s block, and so they have a full s orbital, which makes it a full orbital, or sort of like a full partial energy level, which is a relatively stable configuration. The 5As, do you notice that the P is half full? P fills with 6, and 3, which would be, how many electrons nitrogen, for instance, would have in the P sublevel or orbital. It's half full, and half full is a relatively stable configuration. If you think back to electron configurations, when you do the electron configurations, you would have one up, one up, one up on those 3 different lines. So you've got 1 electron in each of these positions, and that's a relatively stable position. So the 2As and the 5As are kind of special because they have this relative stability where they're sort of like, I don't know if I want to really lose electrons or not. And so you see this little bit of a bobble. But I'm telling you right now, these are exceptions that the AP people do like to pick on. So it's important that you understand them and that you remember them specifically. So again, questions that you have, please bring them to class. Okay, a couple other important notes about ionization energy, or IE. First off, as atomic size increases, the energy needed to remove the electron decreases, and that's because of shielding. So if you compare, for instance, lithium to sodium, to potassium, to rubidium, to cesium, so basically I'm just going right down group 1A, you would see the atomic size increase, and you would actually also see the ionization energy go down, and that's because of shielding. So if you take a look at, say, the size of lithium to cesium, cesium, remember, has more shielding energy levels, which means that the nucleus of cesium is not able to reach out and grab a hold of those electrons in the valence as easily. And so where I gave you the visual before of saying, okay, lithium has its hand out with an electron on its hand saying, please just take it. Imagine cesium's electron is barely even attached to its hand because it's so far away it can barely even get a hold of it. And it's just like, dude, just take it. I really don't want it. Like, I don't even have hardly any control over it anyway. Just take it. So it's going to take you way less energy to remove cesium's electron than it would rubidium, back to potassium, back to sodium, and then finally back to lithium. So the smaller the atomic size, the larger the ionization energy is going to be because it's held a little closer to the nucleus. So, and hopefully that makes sense. Also, note the stair-step line values, which is on page 328 in your textbook, figure 7.5. So what I mean by the stair-step line, do you see the stair-step line in the graphic in the book? And if you take a look at a number that's on the left side of the stair-step line and then a number on the right side of the stair-step line, what do you notice about those numbers? And compare a couple of them. Look on the left and then look on the right of that stair-step line and notice the change you see in individual atoms. So, do you see the change? Like, you cross that stair-step line and ionization energy goes through the stinking roof. I mean, like, not a little, a lot. Like, it jumps up thousands. Well, remember that it's easier, meaning it takes less energy. That's a really fancy abbreviation for energy. Takes less energy to remove a valence electron than it would to remove a core electron. So do you notice for these atoms that are being shown that the valence electrons have relatively lower ionization energies, but once you move into electrons that would be considered core, that's where the energy skyrockets. So again, if you need some help with that a little bit more tomorrow, I can certainly help you with that, and we'll deal with it as we need to. So again, another really big thing to keep in mind. It gets multiple choice questions get picked on with that one a lot. That whole idea of this skyrocketing ionization energy because you've gotten into core electrons. So FYI, very important. All right. So the final trend that we're going to talk about is electron affinity. And it's important that you understand, again, the definition of electron affinity. So between ionization energy and electron affinity both you're going to see that they have the same general trend, but that's because their definitions are actually opposite. So ionization energy, remember, is the energy needed to remove an electron, whereas electron affinity, notice, energy for adding an electron. So do you see that it's an opposite definition? Ionization energy is removing an electron. Electron affinity is adding an electron. So this is going to be a trend then in why they will be sort of similar, ionization and electron affinity in their trend line, but it's again an opposite definition. So answer me this question: which groups of atoms would be very happy to get an extra electron? I'm listening. Okay. So if I heard you right, I heard you say that the halogens, group 7A, fluorine, chlorine, bromine, iodine, they would love to get an extra electron. And why? Right, because they're one away from a noble gas and they would have their octet. So if you take a look at this chart, notice first that the values are negative, and for electron affinity, they're just a little bit different. When we do electronegativity, the values are on something called a Pauling scale. When you do electron affinity, they measure these numbers with negative values. So we're looking at the higher negative values, meaning more electron affinity. Because they're saying it's an electron change. Or, I'm sorry, not electron. It's an energy change for the process. So there's a relative decrease in energy, which means that it's a very, very favorable process. So you'll notice that our halogens have very big negative numbers, and that means that they have a very high affinity, which is just a word that means they like or love. They have a high affinity for electrons. And as you go to oxygen, sulfur, selenium, tellurium, you'll see that they have relatively high numbers also. As you begin to move back towards the back, you'll see that these numbers get a little smaller. You may also notice a similar kind of weirdness. Do you notice that lithium here -60 and then beryllium less than 0? Okay, well, wait, what we just talked about, beryllium is in that 2A group. It's got a full S energy level, and that makes it relatively stable. So does it really want to gain extra electrons? No. Oh, how about this one? Okay, same deal. This is a group 5A. So you can see that we get more negative, and then we go back to relatively 0. And that's, again, because nitrogen has that half-full p orbital, and that's a relatively stable configuration, and it doesn't really have any affinity for electrons at that point. So what that tells you is something maybe contrary to what you've thought before. We've always talked about how nitrogen forms a -3 ion. However, nitrogen doesn't really like to form ions in the first place. It would really rather covalently bond and share electrons with something, and that's evident here in the electron affinity of less than 0. So again, the larger the negative value for electron affinity, the more stable the negative ion will be. So you can see relatively low negative numbers for things like hydrogen and lithium, which means that their negative ions are not stable. They don't really enjoy making negative ions in the first place. So again, electron affinity. If you would take a look at the trend a little closer, and I think, yeah, I actually already talked a little bit about this, so this should be a pretty quick slide. So 1A has a half-filled s orbital. It would be somewhat happy to fill that orbital. So that's why you see a little bit of electron affinity in some of these atoms that you would not normally think of taking on an electron. 2A. Okay, so we already talked about this. They have that completely filled s orbital. They don't want any extra electrons. These electron affinity values are positive, which are these two here. These are nearly 0. No electron affinity at all. It doesn't really have any liking of electrons. If you look from 3 to 7A, so again from, say, boron down to fluorine, you'll see that the values become more negative. The exception, again, is the nitrogen, which we already talked about. And then, and that's the answer. 5A is less than 4A. And then hopefully you can answer that question of why, which is the half p orbital, or half-filled, p orbital. And then you might also notice that all of the electron affinities for my noble gases are greater than 0, meaning that they do not have any affinity for electrons. They don't want them. They don't need them. They got what they need. Octet. Woohoo. All right, so your general trend is to increase from left to right. So your electron affinity is generally very low down here and very high up here. And again, this is related to electronegativity. So two exceptions, 1A is more negative than 2A, 5A is less negative than 4A. So we've talked about that a little bit already. But I do want to pull this in with electronegativity because this is the one that we talk about more in general chemistry. And I want you to understand that they really are very similar. A slightly different definition, but it all has to deal with the want of electrons. To have an electron affinity means you want electrons. And electronegativity, as you can see, ability of an atom to attract electrons. So they really are very closely related. As you move down a group from top to bottom, electronegativity decreases, and that's because they generally want to lose electrons anyway. Excuse me. And it also has to deal with shielding, for that matter. As you move across the period, the electronegativity will increase, and that is because you're moving into more of that anion range where everybody wants to form anions at that point. So sorry, that was kind of quick. Let me bring that one right back up. I thought there was something else, and there just wasn't. Okay, let me get this back up here. So sorry. Okay. So anyway, electronegativity is a trend that you should have learned about last year. Cesium, barium, strontium, rubidium, the ones in the bottom left corner, are going to have a lower electronegativity, where fluorine, oxygen, chlorine are your big heavy hitters, very high electronegativity. And again, if you ask the why question, it all comes back to shielding, effective nuclear charge, and the closeness to noble gases. So basically whether or not they want to gain or lose electrons. So more shielding, like cesium, it's not going to be able to draw any electrons in because it can barely handle the ones it's got. It's got so many shielding energy levels that I can't even grab the ones I have. How am I going to grab anything else? Whereas fluorine, again, is really small, so it can really hold control over its outer energy level, plus it can actually reach out and grab even more because of the smallness of it, and then it can form the octet and then be relatively happy. So this is obviously, it's a lot of information to go over just in one video. My hope is that we will spend a good amount of time in class talking it through, making sure it's clear before we move on to any homework after that. So bring your questions, and we'll see you tomorrow. And that's it. Yippee! Rejoice.